Alright, so today we're going to be talking about limits, and we're going to be using the limit properties and also finding limits using graphing. So we're only going to talk about the first three limit properties today. There are more that we'll address on the next lesson. But essentially what these limit properties say is that if you take the limit of a constant, it's always just going to be the constant. It doesn't matter where the limit is approaching because the limit of the constant is going to be the constant. As for the sum of limits, it just pretty much says that if you're taking the limit of two things that are being added together, you can take each individual limit and then add those two things together and you're going to get the same result. And then the next one says that if you have two things that are being subtracted from each other, if you take the limit of each of those things individually and then subtract them, it'll be the same as taking it all at once. Okay? So let's talk about what a limit is. A limit is essentially evaluating where a function is approaching, but we don't actually care about its destination, okay, once it gets there. So if the function is not defined at the point that we're taking the limit at, it doesn't matter. We're just looking to see where it approaches. So we're going to evaluate some limits using the property of substitution. So these are pretty straightforward. The first one, which of the rules is this one going to be? Go ahead. Yes, it's going to be the constant rule. And since we're taking the limit of a constant, it's just going to be the constant itself. Next one, we're going to take the limit. It's a combination of addition and subtraction. So we're just going to plug in 3 for x. And then we evaluate. So 3 to the third power is
27.
Good. 27 times 2 is
54.
54. That's what you said last period. And then what's oh, why did I plug in a 2 instead of a 3? That was my bad. Sorry.
Don't forget it's -1.
Thank you. That's what you're here for.
I said it. No,
you did too, yeah.
He heard you. He commented off of my comment.
Alright, I heard both of you and you're both valid, okay?
Appreciate it.
What's 3 times 3 times 3?
47.
Good. And then just bring down the plus 3 minus 1. What's 54 minus 27?
27.
So the final answer is
29.
29. So right now it's just doing basic algebra in this stage. Okay. We'll talk about when limits are not this simple in future lessons though, don't worry. Alright, and then the next one, same idea. We're going to substitute and evaluate. What is the limit, or what is sine of pi over 3? Pi over 3 is equivalent to what degree measure? That's sine of pi over 6.
Radical 3.
Square root 2 over 2?
That's 45.
Square root 3 over 2?
Yes.
I did 2 and 3.
Dude.
2 and 3.
We're just
So if you didn't know this, it's from the unit circle. Okay, that's sine of 60. If you don't know it, if you put it in the calculator, it will give you a decimal. So make sure you do know your exact values, at least the basic ones, for your quiz.
Just memorize one part.
Exactly. And you don't even have to really know the quadrant. If you have a calculator and you know what radical 3 over 2 is and the calculator is a decimal, and you know what radical 2 over 2 is, and those, you can use the calculator to help you out. So then from here, to make this into one number, we're going to put this over 1 and find a common denominator, right? So I multiply the top and bottom by 2. So then now it can be radical 3 plus 4 over 2.
Yeah.
Yeah.
Why would you do that? Why not just leave it as is?
Well, I want to show you all the ways you can see it, because if it's a multiple choice question, you know.
Come on, man.
It's not wrong. It's just could be simplified, right?
Wait, are these the exact calculators you have to use on the quiz? Or can I use my own? No. You can't?
No, you're gonna say small.
No, you can use your own, but you can't use a graph.
It's
not a graph.
You got me, Robert.
Oh yeah, I forgot. This isn't.
What?
It's like
Guys, are you still good to go with the rest of this, or Okay, I don't know. Yes, you can use. So somebody was asking about the calculator. This calculator on your desk is the one that I will provide. If you have your own scientific calculator, you can use that. You may not use a graphing calculator. 83, 84. No, I see your calculator and it is a no.
This calculator has a blue line.
Yeah, you don't have to have that one. All right.
That one's
No,
What?
you can't use that one
Why?
because it's a graphing calculator.
Who's
All
your
right,
graphing
because I can see it.
Where? It doesn't
So
even
for
say
the next question, we're going to evaluate the limit where they give us information about the function. So in this one, we're evaluating the limit as x approaches c. So what is the limit as f of x approaches c?
2.
Good. And then what is the limit as g of x approaches c?
Negative 3.
Good. 3 plus negative 3 is?
2 plus negative 3?
2 plus negative 3 is?
Negative 1.
Negative 1.
Are you like a little off today? Are you okay?
You guys are distracting me, so you keep talking.
I'm not lonesome.
Yes, you should be. Alright. Next one. So, g of x, what is the limit as g of x approaches c?
Negative 3.
Good. And f of x?
2.
So what is negative 3 minus 2?
Negative 5.
Yes. That's the answer.
So would it usually like give us like this?
It actually would have to. If it weren't one of the ones above where you're evaluating, you're given a value, you're plugging in for x. If it's using function notation like that one is, I have to give you information about the limit, each individual one, to do that problem. Does that make sense?
Yep.
Okay. Alright, next one. So here we're going to talk about the definition of a limit. The definition of a limit states that if the right-hand limit and the left-hand limit are the same, that means that the limit does exist. Alright, so we're going to talk about how we can figure this out looking at graphs. So when evaluating limits graphically, you must look at the left and the right side of the x value. So basically, when you're looking at a limit, you're basically going to use both fingers and go see where it's approaching on both sides. Okay, that's a full limit. If you're taking a right-handed limit, you go from the right and approach, and then from the left you approach. Same idea. Okay, so taking a limit is not the same as evaluating a function. We do not care if the function is defined at the point of which you're taking the limit of. We only care to see where it approaches. Alright, so let's do an example where we talk about that. I think I can make this a little bigger. Yeah, you probably did do it last year a little bit. Okay, so for the first one, do you see that symbol there next to the 3? It's a minus sign, but it comes after the 3, which indicates that we're looking at the limit from the left. Yes. You're evaluating the limit from the left. So we look at the limit on the left, we look at negative 3 as an x value, and we're approaching it from the left. Okay, and we approach what y value? 1. Now, if we do the same thing, but instead we're looking at it from the right, negative 3, so we're approaching it from the right, we still approach 1. Correct. So, since the left and the right-hand limit match, the limit of the actual thing is, if they match, the limit is what the two limits are. Okay?
But it's the open circle.
The function is not defined at the point, but the limit doesn't care if the function is defined. Limit is where it's going. We don't care what it does when it gets to that destination. Does that make sense? So, to kind of piggyback off that, let's look at g right now. G is asking me to evaluate f of x at negative 3. You see that? So, is the function defined at negative 3? No, it's undefined. So the function does not need to be defined at a point for the function to exist there. For the limit to exist there, I mean. So for the next one, we're looking at positive 2 on the left side. So we look at positive 2 and we approach it on the left. And it approaches what y value? 1. Good. Now if we approach it from the right, it approaches what y value? 2. Good. So do those two limits match?
No.
So the limit does not exist And you can tell because see this discontinuity right here, okay? See how these lines do not match up, alright? So the limit does not exist, alright? Now we're going to evaluate f of 1. So if we look at 1, we're just taking f of 1, simple algebra, not limits. What is f of 1? 1, right here. Good. And f of negative 1.5. So this graph is actually going by 0.5s. So it's actually negative 0.5, right? Do we have any questions about the graph limit evaluations? Okay. Last one. This picture here. So we have 3 different functions. They all have a similar look to them, but there are some differences. All right, let's just talk about these differences in terms of like Algebra 2 knowledge. So the first function has a hole in it, a removable discontinuity is what we call it in Algebra 2. The second function has, basically, it's like a piecewise in a way, okay? The function point at 1 is defined at a different spot than the rest of the function, okay? And then the last one is just a normal linear function. What do these all have in common when we take the limit at x equals 1?
They go to 2.
Yeah, they all have at negative or at positive 1, they all have a limit of 2. You all see that, how the limit hasn't changed for any of the pictures. So that's why it's so important to recognize discontinuity doesn't affect the limit. So on both sides, if I approach, it's still approaching here, even though it's not defined here or here, it's defined at a different spot and it's completely undefined on this one. Okay? So that being said, what can we conclude from that about limits in general? It doesn't matter if
If that point isn't like defined,
defined, yeah, if the function is defined at the point. Doesn't matter if the function is defined at that point.